Go back to the other presentation, the one we started with this afternoon, which is about connections. So after carpentry connections, which are connection obtained by cutting, basically carving the wood and limiting the use of metal fastener to a minimum, now we're going to talk about instead the connection with fasteners, with metal fasteners. As I mentioned before, we have several types of metal fasteners available on the market to connect timber members. We start with nails, chiodi, then screws, viti, toothed metal plates, piastre dentate, then we have bolts, bulloni, tooth rings, anelli dentati, dowels, spinotti, gluing rods, quindi barre incollate, colla, so glue in this case, so we don't use only glue, and so on. So as you can see, we have very different, well, there are many different possibilities to connect timber members. So now we have a look to all of them. Start from nails. Nails have diameters between 1.9 mm and 8 mm. There is a regulation dealing with nails and metal fasteners, this EM 14592. The length is between 30 and 400 mm. The tensile strength is always greater than 600 Newton per square millimeter. The nails may be plain, so we may use the plain shank nails, so nails where the shank is plain without any ribs, or annular ring threaded nails. So this is a photo of plain shank nails, and this is a photo instead of threaded nails. Now next time, on Tuesday, I will bring you here some of those nails so you can touch them by hand and see also the differences. This one, you see, they have more friction because they have this annular ring surface as compared to the other one, which are basically smooth. Then, recently, I very much use what we call as self-tapping screws. So, viti autoperforanti. They have diameters between 3 and 16 millimeters, lengths between 30 millimeter and 3000 millimeter. So we're talking about 3 meter, a screw which may be 3 meter long. Of course, a screw which is 3 meter long is not used for normal structures, used for very big, very large structures. The tensile capacity is up to 60 kilonewton per screw, which is quite a lot. You can think about 60 kilonewton would be 60,000 newton, so 6,000 kilogram, so 6 tons. One screw can resist up to 6 tons. Of course, it's the largest one. The screws may be partial threaded or fully threaded. So this is an example of self-tapping screws, which is with partial thread. So the filettatura here, this thread is partial, only up to a certain length. And this is an example of a screw which is fully threaded. So all the length is threaded. Here you can see other example of self-tapping screws. So the self-tapping screw was a very great invention from the German-speaking part of Europe, because in the past, with normal screws, well, in general, so now with normal screws, as you know, you have first to do a pre-hole. You have to do a pre-bore to 80% of the diameter, and then you can screw the screw inside. Why do you have to do the pre-hole? If you don't do the pre-hole, if you don't pre-bore the wood, what will happen? Have you ever tried to screw one screw without doing the pre-hole? Exactly, this is what's happening. Yeah, need some time because I was lazy and didn't want to lose time to do the pre-op. In this way, you get, particularly if you use screws, you will get immediately a crack. Longitudinal crack. Because if you don't do the pre-hole, as you basically drive the screw inside, you get some tensile stresses perpendicular to the grain, which are going to make some splitting in the wood. So for this reason, you should do first the pre-hole to 80%, and then you screw. This, of course, for more screw. When you go to larger screw, you can actually burn down the driller, basically, because it's too hard to get to do the pre-hole. Okay. Instead, with these self-tapping screws, you don't need to do the pre-hole, at least until a certain diameter, because these screws, they have a certain kind of drill which cut the wood, and they are able to take outside the shaving of the wood. So the shaving doesn't stay inside, but can be basically taken outside automatically by the screw itself. This is a great invention because, of course, this case the preparation is much easier. Every time you immediately screw inside the screw without doing any pre-hole. This is an interesting application. This is a self-tapping screw which can not only drill a hole into the wood, but can also drill a hole into these aluminium plates. Of course, this is a big advantage because if you have to use a connection between wood and these aluminium plates, one of the problems is that, of course, you should do a hole into the plate, but then you need. It's very hard to get when you start drilling the screw to actually get exactly the position of the hole there. So for this reason, without any hole, you just go through, and this is going to cut its own way from the wood and also to the aluminium, which is great. Some other photos about different products. There are several different types of screws available on the market. You see here different trademarks. Most of them are very good. Some applications using dowels, screws, and plates. So very often when we design a joint between timber members, we are making use of steel plates and either dowels or anyway metal fasteners to create a connection like this. This is a nice picture of a bridge using glulam members. You can see here dowels and screws. It's quite a big structure anyway. And then we're talking about dowels. The dowels have the diameters of spinotti. They are basically a cylinder of steel. They are like a bolt without the nuts and without the head, basically. So they're cylinders with the diameters between 6 and 30 millimeters, lengths between 30 and 3,000 millimeters, and tensile strength between 360 Newton per square millimeter and 1,000 Newton per square millimeter. Some photos. You see the nice, very nice connection using dowels, because of course you don't see the steel, you don't see the head of the nut of the bolt. So particularly for the architects, very nice, clean, aesthetic appearance. You see just the wood and perhaps a little bit of holes, nothing more. Here you have dowels and plates, outside metal plates, with this connection, blue laminated timber. Other example, dowel type fastened connections. You can see here very nice appearance with glulam. And then the bolts. Bolts are basically like, more or less like the bolts that we are using for steel structure, except that we will see in this case we need to use much larger what's the name? Washers, rondelle. Rondelle must be much bigger because it's a matter, of course, of contact between a very stiff material like steel and a very soft material like wood perpendicular to the grain. So we need to have a larger, we will see later on, larger washers to diffuse better the stresses from the steel to the wood on a larger area. Then toothed metal plates, they are plates having a thickness between 0.9 mm and 2.5 mm, so very thin, and they are basically forged. Well, they are not forged, I would say they are bends. They are cold formed, I would say, cold formed. You see, there is this, initially there is the whole plates, and then they are cold formed in order to cut those teeth, and they are bent to 90 degrees. Those teeth are used to penetrate within the wood and to provide some connection between different timber members, like you can see here. Some other photos. Perhaps the aesthetic appearance is not the best using these metal plates, and also the fire resistance is not the best. When you expose lots of steel to the external surface, of course the fire resistance will not be very good, because the steel is very good conductor of basically heat. So its fire resistance of this connection is very important. Other application from outside. Tooth rings. So this kind of rings are basically used to connect one member to the others. So this teeth have to penetrate the two members in order to get some transmission of forces between them. And then we have these hidden connectors, very nice invention. As we said, one of the problems of timber is the connection perpendicular to the grain at the contact, between, for example, the secondary beam and the main beam. So the idea of this invention here is to transform a timber-to-timber connection, basically to transform the timber-to-timber contact in the direction perpendicular to the grain into a steel-to-steel contact. So getting rid of this problem of secondary stresses of compression perpendicular to the grain. So we have, you see, this plate here is connected with some inclined screws to one member, and this other plate is connected with some other screw to the other member. Then this part here is locked between this part. So in the end, we have a hidden connection where the compression perpendicular to the grain is not to the wood, but basically it's transferred from this element here to this other element here. You can see here the application. So this is a typical connection with these two plates. So one plate is connected to the beam using inclined screws, and the other plate is connected to the other element, this column, using always screws perpendicular to the grain. Sorry, inclined screws. Why do we use inclined screws? Because we will see later on that by inclining the screws we can get much stiffer and stronger connection than using the screws perpendicular to the grain. Okay, we will discuss at length this later on. So inclined screws can get much higher stiffness and much higher strength compared to screws perpendicular to the shear grain. This is a system that was invented again, always in Germany. So in order to be able to transfer high value of tensile forces, you see they use this kind of metal pipe, which is threaded, è filettato all'interno. It's connected to the wood using these dowels, and it's actually fixed to the wood using a kind of epoxy or a kind of mortar. And then you see there is another cylinder threaded that can go inside here and realize this kind of connection. So those dowels perpendicular to this pipe are made there to increase the strength and to avoid splitting, problem of splitting of wood perpendicular to the grain. So you see the inventor is Peter Bershe, and you can see some explanation. See, this is a grooved drop forged insert, locked into place by intersecting 16 mm diameter tight fit pins. The cavity is grouted solid with high-performance cementitious grout. So in this case, they use a cementitious, high-performance cementitious grout, not even glue, to get a very good bond between the metal and the timber. There are some different sizes, and you can get very efficient, high-strength tensile connections using the system here. Some figures about very interesting connections between glulam members, steel, and you can see here some dowels. You can see also some little cracks here. So this is the roof of a big sports arena using glulam and this kind of connections here. Then, at the University of Delft in the Netherlands, they invented one kind of connection which is called expanded tube fasteners, and which was invented in order to get very high activity and very good energy dissipation for use in the seismic region. In this case, you see, rather than dowels, we are using tubes, metal tubes. These metal tubes have a diameter between 18 mm and 35 mm, and then some densified veneer wood is used between the members to connect. So you can see here, this is a double beam, so a beam made of two cross section. This is a column, and in between the column and the two beams, we have this densified veneer wood, which is a kind of it's a sort of plywood panel, if you want. It's a panel. So one panel is glued on the beam, the other is glued on the column, and then on the opposite side, another panel is glued on the column, another one is glued on the beam. So this is made of densified veneer wood. So you see the density 1,300 kilogram per cubic meter. This densified wood, of course, is an artificial wood, because the normal wood, at the most, they can get up to 600, 700, 800 kilograms per cubic meter, never to 1,300. So this wood is basically artificially compressed. So it's some wood that is put into a press and then subjected to a very high load in order to compress it artificially, to increase its density up to this value. This is an example of a frame using one column, two beams, with these tubes between these 9 holes here, are the holes with the tubes inside, with the metal tube inside. So the advantage of this system is that using this kind of system, particularly using this densified veneer wood, we can prevent splitting, so failure of wood perpendicular to the grain. We have an even load distribution on these metal tubes, and we get a very high strength connection and very high inductor behavior with significant energy dissipation. So in this case, for this, if these connections are used for timber frames, we can use up to a Q factor of 4. Remember, Q factor of 4 is a fairly high Q factor for a seismic design, because it means that you can divide basically your seismic forces by 4 when you do this design, because you rely on a very high energy dissipation within this kind of connection. You see here at the beginning, this is the connector, this is the beam, column, beam, and those are the densified veneer wood. And you see after that you apply the load, at the end, you see that this tube is very much deformed. Very, very much deformed. And of course, the meaning of this densified veneer wood is to make sure that there won't be crushing of woods at the interface with the tube. So in other words, this high density wood is provided to make sure that there will be a failure, ductile failure, on the steel rather than on the wood. because the failure of the wood would be much more brittle than on the steel itself. So on a joint like this, if you go to apply a cycling test, so you measure the bending moment and you monitor the relation between bending moment and rotation, you can see very high energy dissipation. So this kind of cycling behavior is similar to the one you can get on a steel structure. So all the area within these curves here is basically a measure of the energy dissipation that you can get when we do a cycle in our structure. So very good behavior. And then we have these connections using glued-in rods. In this case, what we use is threaded rods, so barrel flettate, which are inserted into holes drilled in the timber, and they are glued to the timber using epoxy resin, quindi resina epossidica. So the idea you see here, you have a column, you have a beam, you drill a hole through the beam, you drill a hole in the column. This hole must be larger, of course, than the diameter of the threaded bars. And then we insert the threaded bars into these holes, and we fill the gap between the threaded bar and the wood using epoxy resin, resina epossidica. In the end, you get a connection which is glued around. You see here the wood of the column is glued to the bar, and the bars are glued to the beams. So we get a connection like this. One of the problems when using epoxy rods is that the epoxy is usually a big component, so you need to get two different substances, and then you need to mix them together with the right proportion, and then you need to apply within a certain time, because if you wait too much after the glue went off before, then you can't really do well with the measure. So one of the problems of this connection here is that they should always be, the glue should always be done into a workshop, never on the building site, because otherwise you have lots of doubts about the final results, because very often the workers on the building site are not trained to do this kind of work. So you see, in a system like this, you are forced to do at least a gluing, one part of the gluing on the building site, because you can't really arrive on the building site with a column and the beams already glued unless you have a small structure. Because otherwise you will have a problem with transportation. If you have a big frame, let's say you have to do a frame which is two-story, two-bay frame, so 6 meters by, let's say, 8 meters or 9 meters, how can you transport? It's not possible to transport. So you are forced to do some gluing on the building site. Inside the system, indicating configuration A, this system can be in some way prefabricated, because what you can do, you can glue the two bars on the column in the workshop, and then you can do the whole of the beams in the workshop, and then you transport the two members of the building site. You can basically connect them directly to the building site by simply slotting down this beam into the column, and then by putting a couple of washers and two nuts here, by tightening the nuts on the building site. So the building site, you basically just need to tighten the nuts of this epoxy rods that you have already the connection ready. An even better solution could be this configuration C, where you basically prepare the gluing of the epoxy bars to the columns, to the beams in the workshop, and then on the building side you connect columns and beams to this kind of steel hub, which in some way resolve the problem of this part here. Because of course the problem is that this part is already the weakest point, because you have that the timber here is anisotropic. So you have some compression, for example, here this compression is parallel to the grain, on the beam is perpendicular to the grain, so you have a problem. So in this case, by removing this part of the beam, you are removing the possible mother of all the troubles, which is the wood here, you're replacing with a steel which is isotropic, so it doesn't have any kind of problems, secondary stresses. Then, of course, this steel hub can be covered by wood in order to improve the aesthetic of the structure. Some examples of gluing rods applications. I can tell you all these pictures are taken from New Zealand, but in Italy, gluing rods are used quite extensively. So you will find very often the use of gluing rod connection, because very often the architect asks for an aesthetic appearance, so doesn't want to see metals, plates, or other things, and of course the epoxy rods are very good in this respect because they are kind of hidden connection. So another connection here, being column connection using epoxy rods. This is a drawing of an epoxy rod. You see here, beam, column, and then you have one epoxy rod here and two here at different distances with a plate in order to transfer here at the moment. Another epoxy rod between this element and the upper element. Very nice experience. And then, of course, one of the problems is to make sure that when you pour the epoxy rods, the epoxy inside the holes, you have a very good and effective glue. Because the problem is that, of course, this connection is hidden. So no one can see, the client cannot see, but also the engineer cannot see. So he or she cannot make sure that the gluing is perfect. So this is one possible problem, because in some way you are not sure that the glue basically can surround all around the surface of the threaded bars and create a good connection. In this case, you are relying entirely on the effectiveness of the glue, of the bond between the glue and the rods and the glue and the wood. So the preparation must be done with some care, I would say. It's very important to be very careful when you prepare this kind of joints. I tell you that in some cases they did some tests, experimental tests of connection like this, prepared in a workshop, and they found very bad results because they found out that half of the length here were not glued properly. So we need to be very careful when we design this kind of connection. That's why I strongly recommend prescribing that those connections there are realized into a workshop, never on the building side. Otherwise we risk even more. So the idea you see here, first of all, you need to make sure that we have a gap between the rods and the hole. So there must be a different diameter. So the diameter of the hole must be 4, 5, 6 millimeters larger than the diameter of the bar. And then we need to make sure that we have a spacer here. So this bar cannot sit down on the back or directly on the wood, because otherwise on one surface you wouldn't get a very good wood. So in order to make this gap, you see here the suggestion to use this wide guide to center the formed dowel in ring hole. So this is kind of filo di ferro, basically wide guide wide as a filo di ferro, to make sure you have this spacing between the threaded bar and the wood around. So we need to use one here at the end and another one here at the beginning of the hole, because otherwise, of course, this will clean down. So this must be horizontal. And then we have to have two holes. One where we inject the epoxy resin, and then another one that is a kind of spy to make sure that your epoxy is inside and has surrounded all the steel. So basically you can assume that the glue is successful when you can see other epoxy coming out this hole. Okay, so you basically you push it this side and you wait for the glue to come inside come out here. So you see here, so this is a plate, this is the real hinge. Plate with a hinge welded, and then you have 1, 2, 3, 4, 5, 6, 7, 8 epoxy rods. You have a hole, the hole where you inject the epoxy, and the other one hole where you expect to see the epoxy coming out once the glue has surrounded all the surface of the threaded bar. We can also have glued connections. Again, also for the glued connection, my recommendation is that the glued connection are prepared only in a workshop, possibly. So this is called scarf joint. This is called finger joint. Then we have large finger joints, and this are called lap joints between different members. This is an example of a very big glue joint that was constructed on the building site. So basically they had to do, you see this was a very big arch made of glulam, combined glulam. So they had to connect this part of the arch with another part. In order to make this connection, they used large finger joints on the vertical surface here. And underneath they cut, you see a wedge, and they glued along this surface of the wedge, all around here. So you see here the gluing was done outside, but you see that they have done anyway a protection. So when you glue something, you can't glue outside with dust and perhaps rain and so on. So they have to construct this kind of provisory structure in order to protect the zone. Then they painted the glue on this wedge. So basically this piece here is this. So the beam basically rests on one side. This beam rests on one side, and this wedge is being now connected to the other two halves, one half here, using this glue. And then, of course, in order to make the glue to go off, to harden, you need to apply some pressure. You see here that they have to use some jacks to apply the pressure, at least for some hours, to make sure that the glue will go off perfectly later. Otherwise, if you don't apply the pressure, you may always have a problem with the glue. The glue can be ineffective. So this is the kind of structure we are talking about, very big, large arch, and this is the connection with the finger joint here with the wedge. Of course, when you do this big glue connection, it's important to do some experimental tests to make sure that the glue is effective. So this is a very big beam that was tested in the laboratory in Germany. Okay, now we start talking about rigid and pin joints. So the first question that I ask you, what are the properties of a rigid joint? So I think we've already been discussing about this, but we can discuss again. What are the kinematic properties and the static properties of a rigid joint? So when can we define a joint as a rigid? What are the properties of a rigid joint? So a rigid joint which internal forces transfers and which degree of freedom allows. Okay, so one joint is rigid if you have no relative displacement between the two ends of the two beams connected together. So we can have this, we can't have this, and we can't have this. Okay? Can a rigid joint move in the plane? Yes. If we have a frame, if we apply the load, this one will in general will move into the plane. The important thing is that there is no relative movement, no relative rotation, no relative translation. Okay, this is clear. This is we define a joint as a rigid if it complies with this kind of kinematical properties. Now, in terms of static properties, so in terms of forces, which forces are transferred through a rigid joint, like this? Which internal forces? All the forces, so axial force, shear force, and bending moment, they are all transferred through the joint. Okay? Clear? Good. Now we talk about a pin connection, or hinge connection. In a pin or a hinge connection, from the kinematical point of view, Cerniera. Okay, so if we have a pin connection, in terms of static for internal forces, the only force which is not transferred is bending moment. If you have a pin connection, bending moment would be 0. Okay? While instead, axial force and shear force would be transferred. In terms of kinematical, so degree of freedom, what can you tell me about the pin connection? So which degree of freedom is transferred, which one is not? Just the rotation. The rotation is free, while instead the axial, relative, we are always talking about relative rotation. So relative rotation of the beam with respect to the column is free. Axial displacement and shear displacement are fixed. They cannot be moved. Okay? Okay, so now we understood very well what is rigid, what is pin. What is a semi-rigid connection instead? A semi-rigid joint. What would be? With a spring, yes. The semi-rigid connection is basically a pin connection with a rotational spring around. Meaning that in this case, we have the possibility, the joint has the possibility to rotate, but it has also a possibility to transfer a bending moment. And this bending moment is proportional to the relative rotation, okay? This is a semi-rigid joint. Okay, so this one, what kind of joint is this? Based on what we have just said. So this one is a column, this is a beam. There are two plates, metal plates, with some, you see, rings of nails on one side, above and on the opposite side. So what kind of joint is this? It's a pin connection, it's a semi-rigid or is a rigid? Your opinion? Are you all sure about rigid joint? Any doubts? Yes, this one for sure can be considered as a rigid one, even though there will be some rotation, but the rotation will be negligible because you can see here we have several lines of nails. So in the end here we have a joint. Strictly speaking, here we have one member, rigid connection between this timber member and the steel. And then we have another rigid connection between the steel plate or steel gusset and the beam. Okay? So this can be for sure, I would say, regarded as a rigid, even though there will be some rotation. The rotation is negligible. So what about this connection here? So the connection between this, let's say this is a main beam, and this is a metal plate with this screws here. So the connection between this beam and this metal plate, what kind of connection is it? Rigid. Why rigid? Can this metal plate rotate with respect to the beam? Well, to rotate it should withdraw the nail there. So it's not possible. If we design well this connection, the rotation is not possible. the connection between this steel plate and this beam here. In this case, as you can see here, there is one dowel here. So what do you think? In this case, it is not fully free, but it's almost free, I would say, almost. To be fully free, you should remove here this plate, and then will be the real beam. In this case, of course, it's not fully free, but almost, I would say. So this is again, it's a kind of example of thinking like that. Okay. Okay. Now, one problem we need to solve, as you can see here we have plenty of ends inside here, so plenty of fasteners. Also here we have several fasteners. So one problem that we need to solve is when we have more fasteners, how can we calculate the stress acting, the force acting in each of those fasteners? This is clearly if you want a kind of hyperstatic problem, because you have more fasteners, you know the global bending moment. For example, here, when you analyze your frame under the load condition, you find out the bending moment here, but then you need to go from the bending moment, which is a general, let's say, which is a general force acting here, to the value of the single force in one of those single joints. How can you solve this problem? This is important because then we need to know these forces in order then to calculate the design of a single, to design a single nail, a single screw. Okay? So how to calculate the force acting each fastener, starting from the global bending moment, global axial force acting on our frame. This is the problem we want to solve now. Okay? So, we start from a simple case. Simple case is if we have no bending moment. So we have no in-plane bending moment and no out-of-plane bending moment. Now, let's try to understand better what we mean for in-plane, out-of-plane. In this case, for example, here you have a bending moment into your beam, right? Now, in this connection here, you see we have different nails along these lines. So in this connection, what kind of bending moment is applied on this connection? It's an in-plane bending moment, it's an out-of-plane bending moment. So this bending moment acting on this connection, what does it try to do on the connection itself? Tries to rotate all these nails with respect to the beam. So how would you define a bending a moment which tries to rotate a number of elements with respect to a center? Torsion, torque moment. So this would be a torque moment for the connection. Can we define it as an in-plane moment or out-of-plane moment? Depends on which plane we are talking about. We're talking about the plane of the structure. It's an in-plane or it's an out-of-plane? In-plane, because this bending moment acts in the plane of the structure and in the plane of the connection, right? Okay, so this one would be a bending moment for the beam and would be an in-plane torsional moment for the connection. Okay? Then if you think about the connector itself, which stress will act in this connection here? So we have you have a number of connectors. bending moment in the beam, bending moment in the connection, and here you have some forces. So this bending moment induces some forces into the connectors there, into the dowels. Now those forces, what kind of stress will mostly induce in this nails here, connecting this plate with the timber? Shear, exactly. So, the beam is subjected to bending moment. The plate is subjected to bending moment. The connection as a whole is subjected to torque moment, inclined torque moment. And the fasteners are subjected to shear, okay, in this specific case. Now, let's have a look to this connection here. Okay. When we apply a load here, we have a moment here. Okay? So this bending moment, in this case will be again an in-plane bending moment, but in terms of connection, if you look at this connection here with this fastener, this bending moment, what kind of stresses applies on the fastener themselves? Before we said was shear here. Here, this bending moment. What kind of stress is going to apply on those fasteners? Okay, so let's say that the beam acts on the steel plates with a force, the shear. This force has an eccentricity with respect to this plane here, so it gives a bending moment. What kind of bending moment is this for this connection? If you look at this connection, it's an in-plane bending moment, it's an out-of-plane bending moment in this case. If you look at the connection, it's an out-of-plane. Because the connection is this time, the plane of the connection is this. It's not a phase. So this bending moment here, it's a bending moment in the plane of the structure, but it's out of plane with respect to the connection itself. Because you see here, the connection is in a perpendicular plane. So this bending moment, it's an out of plane bending moment for the connection. Okay, it's clear? It's clear to everyone, because it's important to become confident with this definition. So, this bending moment here is an in-plane bending moment for the structure, for the beam, for this beam here. But it's an out-of-plane bending moment for the connection, because it acts in the other plane of the connection itself. This out-of-plane bending moment for the connection, what kind of stresses induces in the fasteners? In this case. So, this one, for example, what kind of stress? Axial force. So this one will be subjected to axial force. In English, we say it's a withdrawal, so it's estrazione. And as far as we go here, the axial force reduced, and then we'll have some compression perpendicular to the grain, to the wood. Okay? It's clear to everyone? So axial force here, and then here contact, compression perpendicular to the grain between the steel and the wood. Okay? In order to get equilibrium. Obviously, in the reality, in this fastener, we will have not only axial force but also another stress if we apply a vertical over here. On the equilibrium, which other force will be applied to this? Also, shear. So those connectors, those screws, will be subjected to withdrawal, so say axial force combined with shear. Okay? So we will have to find out a design criterion taking into account that we have a biaxial stress of states. We have axial and shear. We have to combine them together. Okay? It's clear to everyone? If you look instead at these nails here, what kind of stress of state you will have here? We said shear due to the in-plane torque moment. Also here there will be an axial force and a shear as a whole on the frame. So those axial forces and shear as a whole on the frame will induce what kind of stresses into the fasteners? Another shear, only shear. So in this case here, we have that the connection as a whole will be subjected to in-plane torque moment, to axial force and to shear, and the fastener will be subjected only to shear. Instead here, the connection itself is subjected to out-of-plane bending moment and shear, and the fasteners are subjected to couple shear and withdrawal, so axial force. Okay? Clear to everyone? Okay, now we come back to our problem. How do you calculate the force in each fastener? We start with a simple case. If there is no in-plane or out-of-plane moment, so if we have no moments at all, then it's quite simple. Because your axial shear forces are divided evenly among the fasteners. So we just take the axial force and we divide by the number of fasteners. We take a shear force and we divide by the number of fasteners. Of course, this is based on some hypothesis. The first hypothesis, which we will have to comply with, is that we have n fasteners all the same type. So, for example, if we choose one nail, 3.1 millimeter, all the 60 nails for this connection we saw before, they must all be the same diameter. And the same properties, so same diameter, same length, and same steel. Okay? So the fasteners should be all the same properties. Same mechanical properties and same geometrical properties. In this case, you see each fastener, you take the design force, you divide by the number of fasteners. So, axial force, for example, ND, you divide by NFD, and shear force, again, you divide by the number of fasteners. Okay? So, the strength demand, if you have a connection without moment, if all the connectors, all the fasteners are the same, the strength demand in one fastener can be calculated by dividing the axial force or the shear force by the number of fasteners. The other hypothesis is that we should have a symmetric connection. So this fastener should be arranged symmetrically in order not to get any eccentricity around. Otherwise, of course, what we said is not true. Okay? Now, however, now we have a problem. A problem which is quite common, for example, when we talk about geotechnical aspects. So, when you design the foundation, the problem is that actually you haven't done design of foundation so far, so it can be this comparison. So the idea is that if we have a group of fasteners, loaded, for example, in shear, the load carrying capacity of these n fasteners, in general, is less than n times the load carrying capacity of a single fastener. Why is that? Because there is an interaction between the fasteners. Maybe it's easier to think about the foundation. You use some piles, micro piles, underneath a footing. So you have a big footing, and then underneath you use 100 micro piles. Now, if one micro pile takes 1 ton, would say, okay, 100 micropiles will take 100 tons. But this is not true. I mean, it would be true if the micropiles were distant to each other. If they are all together, there is an interaction between the pressure line of each of those micropiles. So they're interacting with each other. In the end, the load carrying capacity of 100 micropiles is not 100 tons, but perhaps it's 80 tons. Because they are close to each other, and they interact with each other, okay? Same thing happens for wood. If we have end connectors, and screws, and nails, in general, the load carrying capacity of this group of connectors is not n times the load carrying capacity of a single connector. Why? Because they are close to each other. There is an interaction between them. Okay, so we need to take into account this phenomenon, because of course if you forget about this, we do a calculation which is not conservative. So in terms of strength demand, we can take the strength demand of all connectors divided by the number of connectors. In terms of strength capacity, we can't just take the strength capacity of a single connector multiplied by the number of connectors, because this is not true. In particular, what may happen is a failure by splitting. So again, in wood, we have this reduction of total load carrying capacity due to the fact that wood is anisotropic. And so you see, for example, here this is a member, this is another member, here we have a plate, and inside here we have a plate like this, connecting the two members. And this plate is needed to transfer any moment around here. So you have an axial force here, tension, the axial force of tension here. So this bending moment tries to open the joint. So this axial force is going to, this tensile force here, is going to create some tension perpendicular to the grain in this direction. And this tension perpendicular to the grain in this direction, if the dowels are too close to each other, is going to produce some cracking. You see that these cracks, this splitting, occurs perpendicular to the grain. This splitting is parallel to the grain. So along those dowels. So this means that if I have to calculate the tensile capacity of these 12 dowels, it won't be the tensile capacity of a single dowel times 12. Because if I put only one dowel here, for sure this crack is not going to occur. Okay? So it will be a reduced number. It will be, let's say, instead of 12, it will be perhaps 8 times. So we need to take this into account. And also we need to consider that this reduction is mostly occurring parallel to the grain. So in other words, if I have one dowel here, and if I have several dowels along the direction parallel to the grain, I can expect this reduction in load carrying capacity. If I have a number of dowels aligned perpendicular to the grain, in this direction I cannot expect any significant reduction, because the splitting here to occur should split the fiber, which is not possible. So we learn from this simple consideration that we have to be careful in order to reduce the load carrying capacity when we have more fasteners aligned parallel to the grain. If we have fasteners aligned perpendicular to the grain, you need to care about this reduction here. We can say, if we have n fasteners aligned perpendicular to the grain, the load carrying capacity will be n times the load carrying capacity of a single fastener perpendicular to the grain. When instead parallel to the grain, I will have to multiply the load carrying capacity of a single fastener by a reduced number of fasteners, which is called effective number of fasteners. So rather than 12, I will have to take 8. For example, there will be some formulas that the regulation is going to provide me to calculate this reduction.
Is there a minimum distance?
Yes, absolutely yes. We will see. There is a minimum distance, so we can't put this one and the other one close here. The regulation will tell us the minimum distance among those dowels. However, in order to not to have this interaction, the minimum distance shall be even larger than what is provided by the regulation. So if you want to have that, if you want to prevent this splitting here, to have that the load carrying capacity of those 12 dowels is 12 times the load carrying capacity of a single dowel, you have to put probably distance 1 here, 1 here, 1 here, much more than the minimum of the regulation. Okay? Yes, it exists. We're going to see. The regulation provides us with the formula. Yes. And the formula will be different for nails, for bolts, and so on. So, F, B, E, F are K, so the characteristic strength in shear of a number of nail fasteners aligned will be less than n times the characteristic strength of a single fastener. This is another example. You see here we have some bolts connecting. We have basically a member like this. This is by doing a cross section. This is a timber beam. Here we have a plate, and here we have some bolts going through. Number of bolts 1, 2, 3, 4. So if they are too close to each other, when you pull here, you get this longitudinal crack. Splitting. So also in this case, the total load carrying capacity is less than 4 times the load carrying capacity of a single dowel. Here, half beam, steel plates between, bolts connecting, going through the steel plates, and again you see the formation of this splitting by the grain. So again, the same kind of problem. So the regulation, if you look at the Eurocode, also to the national CNR regulation, they said that this effective reduced load carrying capacity of n fastener, a line parallel to the grain, will be given by the characteristic load carrying capacity of a single fastener multiplied by n here, effective number of fasteners in line parallel to the grain. And later on we will find some formulas, a semi-empirical formula to work out the number of effective fasteners. Okay? We just have to remember that if we have more fasteners aligned parallel to the grain, we need to reduce the load carrying capacity. Instead, if we have more fasteners aligned perpendicular to the grain, we don't need to do anything. In this case, we can use NEF equal to N, perpendicular to the grain. Okay? Okay, now we try to deal with a slightly more complex problem. Suppose now we have also a mean plane moment in the case of a rigid joint, like the one that we saw before. So if we have a mean plane moment, so a torque moment, like in the case we saw before, we can calculate the forces in each fastener, and this time we won't have any more uniformly distributed load over the fastener. But we can assume that each fastener resists a force proportionally to the distance of this fastener from the center of the fastener themselves. Like we do in steel structures. So, in this case, we will have that the most stressed fasteners would be the ones which are further away from the centroid. In other words, this is the beam, this is the column. So we are doing now, we are looking at this connection here. So this is the beam, this is the column. We connect the beam and the column using this gasket, steel gasket, which is basically a plate out of steel. Okay? Then the plate itself is connected to the rafter using a number of fasteners, for example 6. The 6 fasteners have a centroid. We do always a symmetric system, and there is a centroid. This is the bending moment transferred from the beam to the gasket. Okay, so now we're doing a horizontal cross section here to the steel. So the bending moment from the equilibrium on the beam shall be equal to the bending moment in the steel. Now, we said before, this bending moment can be considered as a torque moment for the connection for the 6 fasteners here. How can we calculate the forces acting in each of these fasteners? The hypothesis that we do is that this force, which is a shear force, like we said before, this shear force will be proportional to the distance of the fastener from the centroid of the fastener itself. So the longer is the distance, the higher is the force. So basically this one, it varies linearly, so it's 0 here, it's maximum here, here is a little bit less because the radius is a little bit smaller. And the second hypothesis that we do is that the direction of this force is perpendicular to the radius joining the fastener with the centroid. Okay? So we do this kind of hypothesis that we said the value is proportional to the distance and the direction is perpendicular to the distance itself. So basically this is what would happen if timber and steel were rigid. So we have a timber beam which is fully rigid. We have a steel gasket which is fully rigid. And the only flexibility in the system is related to the fastener themselves. So the fasteners in this system are regarded as a spring. So it's like having this is the beam, which is considered as a rigid, even if it's not very well. This is the metal plate. And due to the bending moment, we have a rotation like this. So this one is going to rotate rigidly, okay? And the only flexibility is within this springs. So the springs schematizes the flexibility of the joint, of the fastener within the system. So, timber rigid, gasket rigid, connectors, fastener flexible, like elastic springs. Okay, so if this is the case, then we have that it is true what is written here. That basically the force in the fastener is proportional to the distance and the direction is perpendicular to the distance itself. So in the end we can derive, and we will see in a few minutes how, we can derive a relationship like this. For each fastener I, the design force acting the fastener will be the total bending moment acting, torque bending moment acting in the connection, times the distance of the fastener from the central of the fasteners, divided by this is a kind of polar moment of the connection itself with respect to the central. You see, this is a summation of the distances of each fastener squared. Since all the fasteners they are the same, it's like having a mass of 1 times the distance squared. So it's a polar moment of the connection method inertia product. Okay? And if you want, this relationship is formally similar to the Navier equation for bending that you studied in mechanics of materials. So here we have a torque moment rather than a bending moment. Here we have a polar moment of area rather than a second moment of area. Here you have a distance, radius, rather than the distance of the extreme fiber. So, the maximum force demand in the fastener would be, since everything depends on R, would be on the fastener which are further away from the center. So, for example, in this connection here, where can you expect to find the maximum force demand? In this connection here, where can you expect to have the maximum shear force? So, probably, if this is a centroid, either here or here. Okay? How can we derive this equation? Assumption, rigid. Well, this is basically, if you want, it's like a small problem of structural mechanics. We have a assumption of rigid timber and steel plates, which means that the rotation is basically the same. Theta I is constant for all the different points on the gusset. So if we have a rotation like this, since this is rigid, there is a rigid body rotation around the centroid, you will have that for a very small rotation, the fastener will basically move perpendicular to this radius, joining the fastener with the centroid, so they all move perpendicularly. And of course, this distance here will be proportional to, so this movement, the displacement will be proportional to the distance from the centroid. The rotation, since the two elements are rigid, this rotation, theta is the same for all points in the gusset. The other hypothesis that we need to do is something about, as usual in mechanics of material, we always have to write equilibrium condition, compatibility condition, and stress-strain relationship. So in this case, the compatibility or congruence condition is this. Theta is the same for all the different points, which means that the element is rigid. Then, constitutive equation, linear elastic behavior for the fastener, independent of the direction, and with the same properties. So, we have to assume that the fastener will behave elastically, and that the stiffness will be the same in any direction. Is it reasonable to assume that the stiffness will be the same in any direction? But not so much, because if you remember well, wood is not the same stiffness. I mean, in the direction perpendicular to the grain, the modulo of elasticity is how many times more than the direction perpendicular to the grain? I think it's 30 more, if I remember well. So 30 more. So now they're assuming, for example, that you see here, this force here, which is almost perpendicular to the grain, You compare with this force here, which is also parallel to the grain, we're assuming that the stiffness is the same here and here, which is not really true. However, let's say that this problem here would become much more complex if we would start introducing the anisotropy behavior of wood. So for this reason, it is accepted that despite this is not really true in the reality, but with this simplification we can get some results which are not too far away anyway from the actual results, taking into consideration the anisotropic behavior. Okay, it's clear? This is quite a strong assumption we are doing here. I mean, this basically is taken as it is from steel. When you are going to do the exam on steel structure, we are going to design a steel connection, you will do exactly the same demonstration. But of course, for steel it's much more, I would say, logical to think that the stiffness is the same in any direction, because steel is basically isotropic. But timber is not. So for timber it's quite a strong assumption to say that, okay, we have the same stiffness in any direction for our connection. Because in the reality our connection is surrounded by wood, and wood doesn't have the same behavior parallel to the grain and perpendicular to the grain. So for sure there is some differences. Okay? But otherwise it becomes more complex. So we work in this way. So this assumption means that each fastener has a slip modulus of stiffness equal to the slip modulus of stiffness and serviceability limit state. Okay, so. So now we can write that for each fastener, QID, which is the shear force at the fastener I due to the torque moment, will be given by Ki, so the stiffness, the slip modulus, times Ui, which is the displacement. So the relation is like for all the springs. In a spring, the force of the spring is the stiffness of the spring times the displacement. So Ki times Ui. Now Ui, if you look here, Ui, this displacement here, is given by what? Is given by the Ry, this distance, times the tangent of this angle here. But since this angle is small, as you know very well from mechanics of structure, tangent of theta is basically more or less the same as theta because the angle is very small. So in the end, Ui can be approximated by the distance Ri times theta. And theta, as you said before, is the same for all fastener. So in the end, we can calculate the resultant of the bending moment of all this fastener here. So MD will be the sum of the force of each fastener times the distance from the center of the connection. So summation from I going from 1 to n of QID times Ri. But QID we said is Ki times Ui, so Ki is the same as K sub, so K sub times Ui, but Ui is Ri times theta, so in the end you get theta and K sub, which are the same for all connectors, so can be taken outside from this sign of summation. So theta K sub times summation from I going from 1 to n of Ri squared. So from this we can calculate theta, which is our unknown, the hyperstatic unknown. So theta is Nd divided by K sub times this polar moment of area. And then QID again, Ki times Ui, so Ki times Ri times theta. We replace theta with this formulation. And in the end, this is the formula that we have derived the formula that we saw before. Okay? So with this formula, we can calculate quite easily the forces, the shear forces acting into a connection subjected to in-plane torque moment. Okay? So we have already done this remark. We go on. Now, how can we calculate the value of this K cell? So this slit modulus of one fastener that is needed in this equation here. You see, in this equation we have QID is equal to K cell times Ri times theta. So K cell is the slit module of the fastener. The slit module of the fastener is given by the regulation using these semi-empirical equations. So for joints made with dowel type fastener, which is what we are considering now, the slit modulus per shear plane per fastener under surface law should be taken from table 7.1 with rho m in kilogram per cubic meter and d of DC in millimeter. So to calculate the slit modulus of this spring, we need to use these semi-empirical equations. As you can see, those equations have no physical sense. They are the density to the power of 1.5 times the diameter divided by 23. So we need to be careful to use the units that you can find here. So rho m is the mean density of timber in kilogram per cubic meter, and T, the diameter, must be measured in millimeter, the diameter of the fastener. So if you use dowels, bolts with or without clearance, screws, and nails with pre-drilling, the formula is the same. If you use nails without pre-drilling, you have another formula, staples, another one, and so on. So basically, we will be using either the first or the second one. So those are semi-empirical equations, and in the end, if you look at the equation that we found before, this K cell is not needed because, as you can see, in the formula there is no K cell. So when it comes to calculate the forces in the different fasteners, we don't need the K cell. We need to use the K cell only when we talk about semi-rigid connection. So if we have a connection where there might be a significant rotational flexibility, then we need to use this K cell here to calculate this additional rotational flexibility. Because, for example, if you design a frame, if the joint is not rigid, you need to take into account that there will be an additional mid-span deflection due to the fact that the joint is not rigid. Okay? Only in this case, we will have to use this K cell. Otherwise, if you have a rigid joint, or let's say semi-rigid joint where theta is very small, then we don't need to use K cell to solve the system. One important thing is that you see here we're talking about dowels, bolts with or without clearance. The clearance should be added separately to the deformation, usually 1 millimeter. What is this clearance? Is that when we use bolts, there is always a difference in diameter between the hole and the bolt itself. So usually the bolt goes into a hole which is 1.5 millimeter larger. Okay? So for this reason, if you test a bolted connection, you will find that you have initially a deflection more or less equal to this clearance. This clearance will be Gioco for Bullone. So the regulation said that with bolts, the clearance should be added separately to the deformation. You will find later on, we will do a work example of a beam design with a joint in between. Then we will take into account that this additional deflection due to the bolt clearance, so due to this Gioco for Bullano, there will be an additional flexibility, an additional deflection that you will have to consider. Okay? So we will see a work example of this.
Ma le chiese servono soltanto per diciamo, le connessioni non rigide?
No, K-cell is needed only for the semi-rigid connections, not for the rigid connections. For the rigid connections, not needed.
Perché nella formulazione
Exactly. But instead, if you have to calculate the actual rotation, so it can say it's only needed when you have to calculate the actual relative rotation of the joint. Otherwise, not needed. Okay, so we said before, this is the formula for the slip module of fasteners. So joints made without a tail fastener, the slip module per shear plane per fastener under service load. So slip module for per shear plane per fastener. So we will have to introduce the concept of shear planes. So for example, if we have a connection like this, you have one shear plane, because you have a dowel. Your dowel is crossing only one shear plane. Okay? If you have a connection like this, your dowel is crossing how many shear planes? How many shear planes are we crossing now? Dowel. How many shear planes does it cross this dowel now? Two. So here, and S. Number of shear planes equal to 2. Okay? So if you have a connection like this formula must be multiplied by 2 shear planes and by the number of fasteners. So if you have 10 fasteners, you have to multiply 10 times 2 times this. Okay? It's clear? Again, this is needed only to calculate the semi-rigid joint, to calculate the additional deformation. Okay? Not to calculate the forces in the connection. Okay, it's clear? Okay, we said we have to remember if you have a bolted connection with clearance, we need to add separately 1 millimeter with the deflection, take into account this clearance. And then you see if the mean densities of the two joint wood base members are different, then rho m in the above expression should be taken as. So if you have two different types of wood with different density on one side and the other, so for example this is stronger than the other one, in the formula you can put the square root of the product of the mean density of the two woods. Okay? For steel to timber or concrete to timber connection, KSL should be based on rho m for the timber member and may be multiplied by 2. So if you have a timber concrete connection, you calculate KSL using the density of the wood, and then what you get you multiply by 2. You double up, because the concrete or the steel is considered as if it was rigid compared to the wood. Okay? Last but not least, if you need to do some, you hardly have to do this, I would say. If you need to calculate the deflection ultimately state, usually we calculate the deflection serviceability state. So we need this case right here. But if for some reason you need to calculate the deflection ultimately state, then you need to use another value of slip modulus. You need to use 2/3 of the slip modulus serviceability in this state. Okay? This is written again in the Eurocode. Okay, now what's happened if in our joint we have the simultaneously axial force, bending moment, and shear forces? So we need to use the superposition principle. So first, we solve, for example, for the bending moment using the formula that we found before. And we found, for example, this distribution of shear forces around the fastener. And then we solve for the shear. For the shear, if you remember, we said that the shear will be divided evenly among the 6 fasteners. So the shear makes this other contribution. If you have axial force, you do also the axial force, and then you combine the effects. Of course, in this case, you can't sum up them directly because you have vectors there. So you need to use the rule from the vectors. So you compose the vector, you get the final result by composing the two vectors. So the yellow solution are the shear forces around the connection due to coupled bending or torque moment of the connection and shear force. Of course, you use a kind of sin and cos of the angle to find out the final value. Okay? So, lateral withdrawal loads we already mentioned before. As a whole, we can have a connection subjected to shear, to axial force, to in-plane bending moment, to out-of-plane bending moment. But the fasteners can be loaded either in lateral load, shear, or in withdrawal load, estrazione. Okay? This can be clarified with this very simple example here. You have a timber member connected to an angle here with some nails, and the angles are connected with other nails to another timber member. So, this timber member is loaded in tension. This other one would be loaded in shear. So this is subjected to axial force. And then you see those nails here, they are subjected to lateral load. And then these other nails are subjected to withdrawal loads. Okay? If you use bolts, some bolts are, this bolt here is subjected to shear force, and the other 2 bolts are subjected to axial force. So, this bolt here, subjected to axial force, may fail either due to tension in the shank here, or to compression perpendicular to the grain at the interface between the washer and the wood. So when you pull up this bolt, either the bolt fracture in the middle, if it is very small, or you may have compression perpendicular to the grain in the wood at the interface with the washers. Okay? So in this case, we need to check sigma equal to n axial force divided by the area of the washer to compare with the strength of wood perpendicular to the grain. So, design inequality and ultimately the state for the connections. We said before, if we have n connectors and fasteners, n fasteners times q di, so times, let's say, the value of the axial force in these connections, assuming that they are all stressed in the same way, shall be less than or equal to the design strength of a single connector multiplied by a reduced number of fasteners to take into account this interaction that we have between fasteners parallel to the grain. So MEF times this, the design value of a fastener can always be calculated with the normal standard formula. K mod, modification factor for load duration and moisture content, times characteristic strength of a single fastener divided by gamma n, partial safety factor. So we can divide it, both members, by n number of connectors. So in the end, you see that the strength demand in a connector shall be less than or equal to this equation, where we have MEF is the effective number of connectors parallel to the grain, n is the total number of connectors. This is in general for each fastener, and this is the maximum value for the most stress one. So, now we will have to see how to calculate this value here. So, the characteristic shear strength using what we call European yielding model. So, we will find that in the Eurocode 5, but also in the Italian regulation, the strength capacity of double type fasteners can be calculated using some formula that are based, that have been derived in this so-called European yielding model. We should also point out that due to the anisotropic behavior of tools, not always the most critical design condition for the fastener with the maximum shear demand. So in other words, we may have a fastener which is the farthest one from the centroid, which has the highest shear demand. But that fastener could have less capacity, because we will see that this strain capacity depends on the direction of the force. So for a bolt, if the bolt is stressed perpendicular to the grain, it will have a lower strain capacity compared to a bolt which is stressed parallel to the grain. Okay? Instead, we will see that for small nails, the strain capacity perpendicular to the grain will be more or less the same as strain capacity parallel to the grain. So for the nails, we could say that we can go directly to do the check to the farthest fastener from the center of the connection, because it's there where we find QD max, and the strain capacity is the same. While instead for the bolts, we have to check not only the farthest nail, but the farthest bolt, but also other bolts that could be less stressed, but have also less strength because they are stressed, for example, perpendicular to the ground. Non è superiore. Allora, praticamente, la stanchezza comincia a farsi sentire. Allora, praticamente, per i chiodi e le viti di diametro inferiore a 6 mm, la capacità, la resistenza F2RK è indipendente dalla direzione della forza. Quindi la verifica più gravosa la si ha su quegli elementi più distanti, dove c'è la massima domanda di resistenza. Invece per i bulloni e le viti di diametro superiore a 6 mm, la capacità resistente dipende dalla direzione della forza. Quindi non è detto che la condizione più restrittiva sia quella dove c'è la massima domanda di resistenza. Perché se la massima domanda di resistenza ce l'avete parallelamente alla fibratura, lì avete anche la massima resistenza. Ok? Okay, so we just introduced 2 minutes and then we finish. The fastest design equation from Eurocode 5, the one that we're going to use it, we're still using now, was developed in Scandinavia by Johansen in 1949. Johansen developed the yield length theory for reinforced concrete slabs. So he basically developed two topics. One, the line theory for reinforced concrete slabs, which was the first topic developed by him, and then at that time, the most important one. And then, as a consequence of this, also the theory for the design of the timber connection. Now, the yield line theory for reinforced concrete slab, nobody knows because nobody is using. However, instead, this second topic about timber design, nowadays, all the world we are using this kind of theory. So, this equation were derived by imposing the equilibrium assuming a rigid plastic behavior for wood and steel fastener. So in other words, he's using one of the two theorems of plasticity. So there is the lower bound theorem and the upper bound theorem, due teoremi base dell'analisi plastica. So those theorems are based on assuming that both materials, in this case timber and steel, have a rigid, perfectly plastic behavior. So they have infinite ductility. So there are these two theorems. Probably some of you are going to learn those theorems in the course with Professor degli, or perhaps also with Professor Long, I'm not sure. So the lower bound theorem or static theorem said that the solution which satisfies the equilibrium and not the compatibility is a lower limit of the actual failure law. So if we can find, basically for a system like our connection, a solution satisfying the equilibrium and not the congruence, we can say that based on this solution, based on this theorem, this solution is a lower limit of the actual failure law. So we can design for this solution because it will be conservative, because the actual failure law will be higher. However, there is a big question mark here, because the theorem is based on the hypothesis of ductile behavior. So infinitely ductile behavior. Now we know very well that steel can be regarded as a ductile behavior material. But what about timber? Can timber be regarded as a material with infinitely ductility? Not so much, as we said. So we will have to do some testing and to find out under which condition and which kind of failure modes timber may be regarded as ductile. In general, it is not. Okay, so I think it's now it's a good time to stop, and I would say that we stop here.